So I made this video, I did this research kind of out of my own curiosity, and I realized that it would make a good video. And basically, the question is, why isn't AI going faster, and how can we accelerate it faster? But really, this is just a deep dive into what is the holdup with artificial intelligence as of the beginning of 2026. So let's get into it. The TLDR up front is that everything, the biggest kind of barriers is the thermodynamic wall. So power, grid interconnection, physics, that sort of thing. This comes down to the grid capacity. This comes down to transformers on the grid. This comes down to actual generation capacity. So basically everything to do with energy is there. Then there's the supply, which is also structural. Mostly the CoWoS, so the chip on wafer on substrate. So if you see the CoWoS, this is basically the whole package getting delivered. That is now the actual bottleneck. And so this is why like memory is sold out and that sort of thing. So then you have operational friction, which is further down the stack. So this is enterprise execution, data quality, and ROI. And then finally, things like AI safety and security and public opinion, that's actually just noise. So when you have people saying, oh, well, you have to prove that AI is safe, it's like actually, and I mentioned this in other videos and I said that like serious researchers, policy people, nobody takes extra seriously anymore. It's basically just been operationalized. The actual conversation sphere has not caught up with reality, which is really interesting and it's kind of frustrating. And so it's basically kind of become a dog and pony show of like, but Eliezer Yudkowsky said this, and it's like nobody who actually has decision power actually cares. And one thing I will say is that in layer 3 here is, most interestingly, is insurance. And we'll talk about that, but insurance doesn't know how to price AI risk. And that's actually become more of a source of friction than people being like, AI is just slop. Nobody cares that AI is slop from an acceleration standpoint. So next, infinite incentives, abundant capital. What I have always said is that acceleration is the default policy. And there's a lot of reasons that acceleration is the default policy. First and foremost being geopolitical competition between America and China. All the great powers know that artificial intelligence is the defining technology of the next century, or at least the next few decades. And so looking at the past as guidance for the future, America and China and to a lesser extent Russia, although they're not really a player in this, but they all know that artificial intelligence is the way to go. Then you have market competition, which is basically the gold rush of all the big tech companies wanting to get in on artificial intelligence. So you say, okay, well, how much is being spent? So $350 billion annual spend on hyperscalers. So that's basically data centers. $202 billion projected 2025 VC funding. That'll probably be higher in 2026, which amounts to about 1.9% of GDP, rivaling the Manhattan Project. So we are basically living through a decentralized Manhattan Project. So the interstate highway system, the Apollo program, the Manhattan Project, the 2025 and beyond AI build out is similar in scale. We have achieved that. So the idea, however, has been, if we need it, we can buy it. The assumption that money instantly dissolves physical bottlenecks. It's just the bottlenecks are not where we thought that they would be. So that's the level of spend that we're seeing. And the economy is already restructuring around these new problems. So how does that look? Energy is the hardest bottleneck. This is the hardest stop. So the average U.S. interconnection wait is 7 years. So if you want to build a new data center, you have to wait on average 7 years to connect that new data center to the grid, which is insane because that would put us in 2032 or 2033, by which point we should be at like super intelligence and beyond. So the demand is expected to grow from 4 gigawatts total of data centers. And when you say 4 gigawatts total in 2024, consider that Microsoft and Meta and xAI and OpenAI are all trying to spin up 1 to 2 gigawatt data centers, multiple each of them. So just in the next few years, they're wanting to more than double what the current demand was. And so the aggregate demand is expected to hit 134 gigawatts of data center over the next 5 or 6 years. Or I guess the 6 years between 2024 and 2030. It's 2026 now. So we're on track to have 134 gigawatts of demand. For comparison, your average run-of-the-mill nuclear reactor produces about 1 gigawatt. So that's a lot of juice. And I was skeptical about these numbers. I'm like, it can't possibly be that much. But when you look at the rate of build out and the amount of backlog, like, yes, this is not hypothetical future demand. This is basically what is on deck and what people are trying to get permitted and approved right now. We're going to hit that and we might exceed it. That's, of course, speculation on my part. We might not hit that, especially if we find new efficiencies. But energy is one of the biggest bottlenecks. Now, there are solutions that didn't make it into this presentation. So like microgrids, where you have a combination of solar, batteries, and natural gas turbines on site. That's one answer. Directly connecting nuclear power plants to data centers so that they're not attached to the grid. Basically, the grid is the bottleneck. So a lot of what these companies are doing is becoming their own utility companies as well. And we've seen this. Like there's a site in the far east of Russia where there's a natural dam, or not a natural dam. They use hydroelectric to power aluminum smelting, and the energy is just used primarily for the aluminum because it's really expensive. So that's the only reason it exists. Now, obviously, we don't have Siberia in America where we just have thousands of miles of unused space to spread out like that, but we do have lots and lots of desert so we can build solar in that. Anyways, riffing on just a little side tangent on where things are at in terms of energy. So next is physics. So this is the highest latency part. So the idea of getting the grid, because we've got the whole United States to power. So getting the grid up to speed is going to take a lot of time and a lot of work, because that means new transmission lines, new transformers, and that sort of thing. The transformers themselves, the lead time is up to 210 weeks, which I thought was nuts. 210 weeks. So for comparison, a year is what, 56 weeks, 54 weeks? I don't remember off the top of my head, but that's basically 4 years almost. And these are not the little transformers that you see at like the power substation. These are the gigantic transformers that you don't see. These are the house-sized transformers. And so we've got a backlog of those in demand. And then the nuclear delusion. So the idea is that the earliest that nuclear could get spun back up is like 2030s. So what really is emerging from the data and the research is that the crisis window is going to be over the next couple of years. So 2026 through 2028 is really when it's going to be the hardest, because as the infrastructure projects ramp up and as the orders for transformers ramp up, those will eventually get solved over the next 2 to 3 years. But nuclear is not going to get solved that quickly. So small modular reactors, they're going to be too late. So what we really need is stuff that you can spin up very quickly. So that's natural gas turbines, that's solar, that's grid scale batteries. And we do have cheap grid scale batteries now, which is the iron air batteries. So if you haven't heard of those, they're not very efficient, but they're dirt cheap and they last forever. And when they don't need to be portable, they can be really heavy. So iron air batteries are probably the way to go, if I had to guess, as the best grid scale battery technology. Because a lot of people are like, yeah, but you need to cover base load. It's like, you don't really need to cover base load if you have enough batteries. And that's, solar, right? A lot of people say, well, solar can't do everything. Solar can do everything when it's combined with grid scale batteries. So moving on. The supply chain. So this is interesting. GPUs are no longer the bottleneck. So the logic dies. So that's the actual wafer. That's no longer the bottleneck. High bandwidth memory is now the bottleneck. So this is sold out through the end of the year, which is why people are making memes about how expensive memory is. And part of the reason for this is that all the companies that can make memory, instead of making memory for your laptop and your desktop, they're saying, well, we can make a lot more money on memory for the accelerator. So we're going to make memory for that instead. So this is basically a price signal saying, hey, we need a lot more memory. So the people who can make it are abandoning it. So the legacy DDR3 and DDR4, they're abandoned. And that means that robots, autos, laptops, and that sort of thing are all facing memory crunches. AI nodes, so the hyperscalers are consuming all of the available capacity to build memory. And then NVIDIA books greater than 50% of all CoWoS capacity. So that's the chip on wafer on substrate. So what we're seeing here is the entire package. So if you hear packaging, this is the GPU, the onboard memory, the high bandwidth memory, and then the rest of the substrate that you put it on. And NVIDIA is booking most of it. So NVIDIA is dominating this space as well. It will take time. Remember a year or two ago, we said, oh, we're going to have a GPU shortage. Well, it took a year and a half to 2 years to figure out the GPU shortage. So now it'll take another year and a half to 2 years to sort out the bandwidth and substrate shortage. There we go. So those are, again, the market will fix these problems. That's kind of what I want to drive home here is energy. This requires state intervention. This requires lots of cutting through red tape. This is not something that the market on its own will sort out post haste. This needs regulatory help. This is purely market. So the processors and the memory, the market will sort that out. It'll just take time. Now, the other bottleneck is data. So people keep talking about data, and the thing is, I'm not convinced by this argument because we're seeing a very, very sharp rise of synthetic data. However, it is still a concern because AI trained on its own data does tend to result in model collapse, but the latest generation of AI models are trained on more and more synthetic data. So I'm not convinced that this is actually going to be a bottleneck. Now, at the same time, it is true that the amount of raw human data, we're going to run out of it. But as many of you have pointed out over the past, humans do a lot more with a lot less data. Like a human brain is trained on like less than 1% of the amount of data that an AI model is trained on, and we're still better. We're still smarter. So we are clearly doing something different. We're not getting the most out of the data that we have. So, and I always say like necessity is the mother of invention, but constraints are the father of creativity. So if we run out of data, I'm convinced that we will find better algorithms to make better use of the data that we do have, because we clearly have enough data to generate, super intelligent human level performance. Again, if a human can spend, just 20 years or 30 years learning less than 1% of the data that we do have available and advanced physics, then AI should be able to do the same. So AI is just not that efficient at learning. So we will get better at making AI learn. So again, I don't really see this as a barrier, but this is one of the things that came up in the research that people are concerned about. So I wanted to at least include it. Now, the $600 billion question. So this is the infrastructure spend and the ROI gap. The market rotation. So investors are fleeing infrastructure for software productivity. This is the most interesting thing where investors are getting more and more wary of, hey, write me a check for $100 billion to build data centers. When are the data centers going to turn a profit? Oh, maybe 5 to 8 years. Investors don't like that. They want to see returns on investment very quickly. So the hyperscalers that raised $100 billion in debt in 2025, the investors are starting to look askance at them, which is why you see Sam Altman going to places like Saudi Arabia saying, hey, can you finance our data centers? The question, can spending 20% of GDP sustain on belief alone? This goes back to the bubble fears. So, yes, some of the most profitable companies on the planet already are using AI, although you might say, well, where's the evidence? We're in Solo's paradox or the J curve of productivity, where AI is the perfusion is happening. AI is getting into the market and it's saturating. But, while most companies are using AI, it's not saturated to the degree that you'd want it to be saturated because it's simply still too expensive. In the same way that in the 80s, the personal computer was not as mature as it is today. It's like, okay, you have a PC on your desk and it, has a monochrome screen that can connect to a central database. Great. That's definitely more productive, but it's not nearly as productive as even just a cell phone is today. We are at that era where, yes, it's there, it's useful, but it's not saturated. So it'll take another few years to really find all the uses to saturate the AI. But in the meantime, scaling up the production of the AI. So we've got this log jam between it's not as mature as it could be. It's still expensive to run. And this is also very similar to early internet, where, when you still had like dial up and ISDN and that sort of thing, then you had to, ISB in his book, the ISDN, I'm remembering incorrectly, DSL basically, digital subscriber lines. So when the internet was new, it was useful, but it was still too expensive because the cost per packet was too high. Now, of course, the internet is basically free. You just have a flat monthly subscription and you get as much internet as you need, and it's at gigabit plus speeds. So it'll take a little bit of time for us to build up that much infrastructure until the point that AI is just kind of a background expense and you're not thinking about the cost per token. So, and in the meantime, the enterprise ROI is not necessarily manifesting as quickly as they would like, although most business leaders understand that AI is very competitive and compelling and that they need to not be asleep at the wheel. So then, of course, the ROI is about, why 88% of pilots fail. And of course, this is different from the 95% of pilots that fail from the MIT study. I've talked about this plenty of times, but I'll go over it briefly, which is basically most pilots fail. AI is no different. That's the point of a pilot, is to see, can we realize value? So you start with 100% of AI pilots that you initiate, integration complexity and data mess, and then 12% reach production. So that's still better than the 95% from the MIT study, but it's still the vast majority fail. So what are the barriers? Number one is data quality. And getting good data is always the problem. And getting good data integration and data governance is always step one. Number two is integration with legacy systems. This is another thing, is big companies are running stuff that is 20, 30 plus years old. And many of them don't even have modern APIs. Some of them don't even have modern operating systems. Some of them are running on old operating systems like SCO Unix. And then they also have a lack of talent. So the lack of talent, the lack of integration, the lack of being AI ready, it has nothing to do with safety or ethics. The barriers are very mundane, which is cost and ROI, and then also insurance, oddly enough. So then when we say what actually gets talked about, so the vast majority of public opinion about AI is safety and, AI art is crap. But what about copyright, and what about the actors, and general regulation about consumer protections? That's where most people are talking. That's where the conversation is. But the reality is that it's like less than 5%, of what actually gets discussed. So frontier labs accelerate despite the resignations that happen. Why? Because there's a lot of money to be made if you're a talented AI engineer, and there will be for a while. One of the numbers that I saw is that there's about 22,000 high-end AI engineers out there, which is just not enough. So if you want to make bank in the next few years, become a crack AI engineer. And help with the acceleration. That's one of the biggest bottlenecks that any individual can help overcome. B2B adoption ignores public sentiment. So this is basically like, yeah, you guys can whine about AI art and all this other stuff and copyright infringement. The businesses don't care. It doesn't impact them whatsoever. And then US federal regulation is largely noise. So the EU is slowing things down, which is like, okay, Europe, you're hurting yourself to, I don't know, spite America. I don't know. But the regulation is not really slowing down artificial intelligence. Neither is safety discussions. So, however, where regulation is the real friction. So number one is the US-China rivalry. So there's export controls and import controls. And this is, if you take a step back and you say globally, what is the barrier to friction? And it is the compute gap. Already, America has like 2 to 3 to 4 times or 5 times the amount of compute that China has, but our compute is pulling ahead of Chinese compute, not only in terms of quality, like per unit quality, but overall volume, which means by 2027, America is expected to have 17 times the compute of China. And that is due to export controls, which from a geopolitical perspective, that means America is winning. That's our moat. Now you might say globally, that's not a good thing because that slows down Chinese research. Although, as I said, constraints are the father of creativity, and the Chinese are very creative. They're able to do a lot of research with a lot less resources. Now, when you look at the Center for AI Security and Innovation, which is that the one that is the subset of NIST? I think that's the department inside of NIST. Their studies basically show that the Chinese models are inferior across the board. Some of them are cheaper, some of them are more efficient, but in terms of cybersecurity risk, they're much higher. In terms of intelligence, they're not as good. So they don't really represent a threat on a military level. Then you've got the EU AI Act. So this is the brake. This is the compliance wall. So the licensing cost for any high-risk systems is $52,000 a year, which means that you're basically going to stifle any startup. No startups dealing with higher risk AI use cases will be in Europe, and this is already true. And so where do they go? They go elsewhere. They go to America. Some of them go to China. Some of them go to Saudi Arabia. Basically, Europe is very good at ensuring that frontier business does not happen in Europe, which is kind of silly in my opinion. It's like, they're very, very proactive, and there's a lot of regulatory capture and what I call a vetocracy. So basically the Department of No, that's what Europe is. And then finally, liability. This was the most interesting finding from my research, is that many insurance policies have absolute AI exclusions, meaning that if you use AI and there is, if there's an OSHA violation, if a patient dies, then the insurance company completely washes their hands. They say, if AI touched that incident, we are not taking any responsibility whatsoever. And the reason is because it's new, it's high risk, it's high variance. They don't know how to price it. I used to work at a workman's comp insurance company. When you have and this was at the very beginning of my career, when you have a domain that is well understood and the risks can be controlled, and understood and measured, then they know how to price it. And so like we had a division of our insurance company that would handle like the one-off cases where it's like, oh, hey, you're a physician who operates out of a yacht or something like that. Like, because you have onboard physicians. And that is not as well understood as a physician operating in, say, a hospital or a clinic. So then it's like, okay, well, how do you ensure a physician, if they're working under suboptimal conditions on, a really expensive yacht and with really expensive clients, how do you price that insurance policy? And so you can price those things, but it takes a lot of work and a lot of effort to do a one-off. And that's not how you operationalize and how you scale. So likewise, when you have your average corner store or your mom and pop shop or your average enterprise that really just wants a templated insurance policy to say, hey, we're using AI for this, make sure it covers our customers, make sure it covers our own butts. The insurance company says, we don't know how to price that. And so we're not going to cover it. And we're going to ensure that our policy has an exclusion saying we will not be on the hook, and if there's no insurance, then the companies, then the enterprises simply won't do it. And so this is, I think, the most ironic kind of barrier, legal friction for adopting AI. So if I have any insurance people, any insurance pros in the audience who want to like help explain how we could make this better, I think that would be great, because this to me is the dumbest reason to slow down AI. I get it, but it's like, really, like because we don't know how to price it, like, moving on. So what this is being called, this phase that we're in 2026 through 2028, is the digestion phase. So the hype cycle was 2023 to 2025. Now we're catching up with reality. So reality says, we need grid interconnects, we need transformers, we need high bandwidth memory, we need the chips and wafers, we need verifiable synthetic data, and we need to figure out the insurance policies. So it's now from bigger models and scale is all you need to efficiency and distillation and make do with what you've got. Just do the best with what you've got. And that's the paradigm that we're going to be in over the next couple of years. Now, that's not to say that no new capacity is coming online. Obviously, there's new capacity coming online all the time. But we're not, the distance between what we would like to install and deploy and where we can actually deploy is still growing. So then after 2028, that's when acceleration and the economic pivot will continue. So the friction map. So this is basically a recap, is the critical and binding constraints are power availability, grid interconnection, and HBM supply. Moderate and addressable, so that's data quality. Again, I'm not concerned about that. The packaging, that seems like it's going to be solved by the market. Deployment friction, again, that it just takes time for enterprises to learn how to deploy these things and to operationalize it. And then liability, the insurance liability, this to me is the silliest thing. The things that are not a friction, at least for America, is number one, safety and X risk. Number two, federal regulation, and number three, capital availability. So that's a really interesting place to be. There is no bubble to speak of. There are frictions, but as I've talked about in previous videos, the difference between a typical bubble and what we're seeing is everything is sold out, meaning we still have unmet demand. With a bubble, that's pure speculation. With this, it's like everyone wants more AI, and AI is not even like at its prime time yet. It's not even fully matured yet, and people want more than we can give them. So this is very, very different from a bubble. And that, I believe, is it. So atoms eat arguments. To accelerate AI, stop arguing about philosophy and start pouring concrete. The future belongs to those who master the physical world. Grid permits, fab capacity, energy generation. Focus on atoms. And then we have the sources and references. So with all that being said, thanks for watching to the end, and I'll check you all later. You are now aware of why AI is going to go slower than we would prefer over the next few years, and it has nothing to do with the actual research being done. The research is continuing apace. Now we are entering where the phase where the rubber meets the road. So the friction with reality is the barrier now. Cheers.